artificial intelligence. Tonight we have a mathematics talk by Dr. Raymond Puzio, who is not only a longtime LIST NYC member, but also a close personal friend. He got his master's degree in mathematics and physics at Columbia University, and then went on to Yale to get a PhD in mathematics. He also runs an organization and a website called Planet Math that is geared to promoting and teaching, helping people with mathematics. They put a lot of mathematics books online on Planet Math.
Including the book from tonight.
Including the book from tonight. So can we please have a very warm welcome for Raymond Puzio.
Thank you. Actually, so just for reason I move this up. Just give the projector a moment to warm back up again. Okay, is it ready? Uh-oh. Okay, just gonna move this a little closer so I can closer to strongest for as my leash.
I will move out so that you can.
Oh, sorry if you don't. Yeah, because I take this place so I can be a little closer to the board. Okay. See, it's claiming to have something.
You may want to move back a little bit.
Okay.
I guess you're doing.
Well, I'm not blocking this projector, so that's good. Let me see though why it doesn't want me to move. 1 minute, I have to do this. Sorry, because it'll take a few months to reset this the way it should be. And then we'll have, okay, good. Yeah.
Oh, one more thing, guys. If you are a male and you would like to go to Closure Bridge, you can actually attend if you're accompanied by a woman.
All right, so with that note, here's my talk. So I've called it Hot, What I Learned During the Past 4 Years. So the idea is the past 4 years refers to the fact that, we've had a study group for this topic that was actually organized by 2 people from here, Gershom Bazerman and Dustin Mulcahy. So they organized it. We've been studying this and related topics. So part of what I'm going to do tonight is try to summarize in an hour or so the type of things we've been doing. So I won't be able to go into technical details or get very deep, but at least give you sort of a flavor of some of these developments in foundations of mathematics that we've been studying. All right, so I'm just go quickly over the things. So okay, so I'll introduce it, and I'm going to talk a little bit first about what one means by foundations of mathematics. Then going to go into, all right, and then talk about several approaches to them. First, there's the classical approach of set theory. Then there are these new approaches with types and categories that constitute this subject. Then I'm going to go into a little bit of how each one works. So look at logic at different levels of propositions, and then of predicates, show how the new approaches differ from the old ones, and finally end up with a little discussion of equality and logic. So first I started by saying the acronym. So what does this HOT mean? So originally it meant homotopy type theory. So what that was is that what that means to define. Homotopy is a branch of geometry and topology that studies things by asking what happens when we do one parameter deformations. So you have some space or whatever you have, and then you imagine that I have a change of it depends on one parameter. Simplest case would be if I had a point. If I have a one parameter definition, well, the point will move and it'll trace out a path. But instead of a point, it could be a subspace or a function of the space. So it studies such things. Then type theory is something you've heard about probably from types in programming languages, which is basically a branch of logic. And what happened was that starting around 2006, people noticed certain interesting connections between the two. And in fact, there was a whole group that met at Princeton to study it and published this book called Hot or Homotopy Type Theory. And like I said, then what we did was, about 5 years after the book came out, we met and we spent, a long time trying to figure out this book. All right. Now, and we actually succeeded. After 2 years, somehow or another, after meeting every other Wednesday of the month for 2 years, we actually made it to the last chapter of the book. And then we moved on to another book, which is MacLean's book on topos theory. So I'll tell you a little bit what topos theory is later. You know, it's another, all right. But we decided, since we had changed that, we need to upgrade the acronym, since we got a new book. So we've upgraded it to, you know, you could say homotopy or topos theory, or homotopy, types, and topoi, however you prefer. So it will include this. And as you'll see, all these topics are closely related. All right, so next, okay, I apologize, I was a little bit short on time, so I didn't get to put examples in. I'm going to post this as I have. I'm going to post this on the net, and in about a month I'll have an upgraded version that has more examples and pictures. But if you bear with me, oops, well, okay, that went too far. Yes, we'll get to that, but yeah. So, you know, so first saying, what do we mean by foundations of mathematics and logic? So basically, one way of looking at it is that we have 3 levels. First level, we have, you know, propositions. So for example, proposition might be, you know, it's rainy or it's, you know, clear or whatever. And then what do we do with propositions? We can connect them to with connectives. So then we can say, you know, if it's rainy, I carry the umbrella. Or if it's, you know, raining and I'm outdoors, I carry the umbrella, etc. And then what it studies is basically how do, you know, if you know the truth in whatever sense of a proposition, how does, you know, how can you figure out the truth of a compound proposition that's made with connectives? Then next level we go is predicates, which is a level at which we say, well, instead of just having propositions, we say that now the proposition can depend on something, and we can ask, you know, is it true for all things or some things? So, and there are more advanced examples where you can have quantifiers that tell you, well, maybe this is always true no matter what, or it's necessarily true or not true. So the idea is that there we're implicitly not just saying I have a single proposition, but it can depend on something, and I can, you know, so I can ask, is it, you know, does exist something that makes this thing true? Let's say there exists, you know, an umbrella in this room, or there exists more than one umbrella, or maybe there's a unique umbrella, etc. And then finally we have level connections, where we deal with collections of objects or sets. So roughly speaking, that's one way of thinking of what people mean foundations of mathematics. And basically the thing started in the 19th century, you know, and what happened, you know, all right, let me just scroll up for that though a bit. So started in, okay, got a little bit off the screen left, okay. So it started in the 19th century, yeah, sorry.
I'm sorry, those collections,
Yes.
can you make statements about them?
Yeah.
Okay.
Well, sure. And then you do things like, you know, what's the intersection of two sets, etc. Yeah, that's right. So I just mean, so the original approach to foundations, yeah, sorry.
Is predicate logic an extension of proposition logic?
Sure.
Okay.
Because if you take predicates that have no variables, they're just plain propositions.
Okay, cool.
Or if you take a quantifier, let's say if I have a predicate p of x, then if I take, say, all x p of x is a proposition, because I've quantified out the variable. So if there's no pre-variables left, they become propositions. And then sets extend it, because see, when you have a quantifier like all x, you know, what do I mean all x? Probably if I'm talking about, you know, umbrellas in this room, I'm only thinking of, you know, maybe relate to the city or something. So now in set there I can say for all umbrellas that are in New York City, one of them is in the room. So you can, because when you have predicates, they just vaguely talk about some, you know, universe or set, but now it's set there is a level we can make it specific which one. So, like I said, so the original approach to foundations was, well, what's known as classical set theory. So it was, you know, started in the 19th century, basically developed starting with Boole and then sort of brought to completion by Russell. And, all right, so this is, and as it turns out, we already had a talk here at LISP New York about that by Lou Thrall 2 years ago. So don't worry, I'm not assuming everybody was there at the talk, so I'll summarize the important parts here, but, all right, so that's the original approach. We're not going to do much with it other than mention it's there and use the contrast to new approaches. because I said that was developed, from say, mid-1800s up to say 1920. But then in 1920s and 30s, there happened an explosion where people like Gödel and Łukasiewicz realized there are many more ways of doing logic than just the old classical way. And what we're going to talk about is two of those new approaches. So one of them is, type theory. And again, we had a talk about that on here by Gershom Bazerman, what was it, two years ago. And basically, this was developed by, people like, started actually with an idea of Russell's, developed very much by Church, who invented lambda calculus. In fact, lambda calculus is part of this approach to logic, and we'll see lambdas soon enough. So you can rest assured that I'm giving a talk in the right room. And then, all right. And the third approach, which is much later, it's called category theory, even though, as it would turn out, we actually had the talk on that in Lisp New York before the other two. This was actually originally developed in the 1950s as in connection with geometry and topology, but then a fellow named Bill Levere came around 1970, figured out that this actually could be adapted to study of logic. So this will be a third approach. As it turns out, it will turn out, as I'll show, part of the thing will be to show how actually type theory and lambda calculus and category theory are actually very similar. They have a, if you understand the right way, you see they're really describing the same thing and taking the same outlook on the subject, which is actually quite different than the old view from set theory, classical set theory. All right, so now I'm going to say a little bit more about each. So no, I'm not going to try to repeat the three last Lisp New York talks. I will condense it down to a few minutes each. So one way of thinking of these three is to say that when you work at that third level of collections of things, there are three basic notions you have. One is the notion of I have some elements which are things that can go into a collection. Then of course I have the collections themselves, and I also have functions or mappings that can take one collection into another, or elements into another. And one way of thinking of these three approaches of foundations is that each one sort of puts an emphasis on one of those three things as the basic operation and derives the others from it. So let me say what that means. So in set theory, the basic thing we take in mind is the membership relation. So this epsilon just means, that, A and B, epsilon B means A belongs is an element of the set B. And the point is that everything else is defined in terms of this relation. So for example, if I have S1 and S2, what do I mean for them to be the same set? They're completely characterized by what belongs to them. So if S1 and S2 have property that anything that also belongs to S2 and vice versa, they're the same set. The set doesn't have any other structure beyond that. In other theories, that may not be the case, as we'll see. But in classical set theory, we assume that. Further, and similarly on functions, we assume if I can tell you for every possible x what f of x is, or that it's not defined for that x, and for two f's, whenever it's f1 of x is defined, f2 of x is defined, and they're the same, then I say they're the same function. Now, this, by the way, was already controversial in the 18th century. The reason is very simple. Usually, how do you specify a function? One way is I give you a table of all values. Another way is I give you some rule for computing it. And it could be I could have two completely different looking rules that actually, when I apply them, gives me the same result, right? I could have two programs that compute the same thing, but maybe they just compute different algorithms. They're written in different languages. They don't look at all like each other. And as I said, this was actually already debate, between Euler and D'Alembert, where D'Alembert took the point of view of no, each rule is a separate thing, and if I have two different programs or two different copies, they're different functions. Whereas Euler said no, anything, all that matters is the output. So that debate actually, already had roots in the 18th century, and it came back in the 20th century. So in particular, classical set theory took Euler's point of view that all that matters is what it does to elements. And we'll see that, all right. And then the final thing is that, how do we make set theory work? Well, we need to have a way that, first you might, in your axiom, specify some very basic sets, like a set with one element, a set with, natural numbers, etc. But then we need a new way, if the theory is to be at all interesting, we need to have a principle that then creates new sets from the old ones. And the basic principle we use there is what's called comprehension. That if you have a property, I can construct the set of all things that satisfy a property. Now, turns out, and Lou discussed this when he was here at Lisp New York, you actually have to, qualify when you can do this so you don't get into paradoxes. But if you set up set theory correctly, it tells you, here's a set of rules when I can do this. And this will be the basic method for constructing anything in set theory. To take property and construct set of things with that property.
What is the property?
Oh, okay, it would be the same as, be a proposition, would be a predicate. So for example, property might be that, let's say natural numbers, property is that the thing is divisible by 2. So I construct a set of all x such as x is divisible by 2, otherwise known as even numbers.
What if there's no property? Just a random set of things.
Right. Well, so then you have to, so then usually what you'd get is, depending on how you set theory, you may have a universal set, in which case there's no property, I get all elements of that. Or if I don't have a universal set, if I use a different formulation of set theory, I'm only allowed to use this principle saying I begin with all things of an existing set that have this property. Like my case where I started with a set of all integers, then selected from that. So, yeah. All right. So now, next we go to type theory. So as the name suggests, the fundamental notion there will be a type. And a type is is also, sort of philosophically also some sort of a collection, but they'll behave much differently than sets. So, and the other notion is a term, where by a term we mean an expression, and specifically it'll turn out to be a lambda expression. So this is basically, you could think of as a formulation of, something like D'Alembert's notion, where he said, no, don't just give me an abstract function, tell me the actual rule I use to compute it. And in here, like I said, the terms will be lambda expressions, which if you like, you could think of as Lisp or Haskell or whatever your favorite language programs are. All right? So the idea, the first place where this differs radically from old-fashioned set theory is that in set theory, we assume that they were just things floating out there. Whatever they were, number 1, triangles, squares, and I could just make sets out of them. And in particular, a thing that's out there could be an element of one set or no set or any number of sets. Whereas in type theory, it's much more strict. Everything must have a type, and it can only have one type. So for example, and this you're familiar from strictly typed languages. For example, if you took, say, the number 2, you could have a set theoretic formulation where 2 might be an integer or a signed integer or a rational number. But in type theory, you would say, no, those are really 3 different things. And if we want to, convert one another, right, if you were in C, you would write, what is it, float star n to turn the thing into a float. And in type theory, similarly, you'd have to have some function that would take, say, the integer and turn it into a rational number. You couldn't just, like in set theory, assume that this thing belongs to both the set of naturals and the sets of rationals. So that's the first main difference. Then the way it works is that to make new types of old, instead of using the set of comprehension, which wouldn't really make sense here, because obviously if everything belongs to one type, I can't construct a new type just by taking elements out of it and saying they belong to the other type directly, because nothing can belong to 2 types. Instead, I have to use constructors to do it. So, for instance, one example of constructors, if I have 2 types A and B, I have the constructor arrow, which gives me then a new type, A arrow B, whose elements are going to be all functions from A to B.
Why are types necessarily disjoint?
Oh, okay. I mean, it's just a basic axiom of the thing.
Okay.
Is one way of putting it. Well, but maybe Jay has a better answer.
This is the paradigm vision type theory. And so, of course, in actual type theories, in effect, you can have one type be a subtype of another. But this is the vision.
Right.
Okay.
That's right.
Everything presents, having associated with it, a type. And everything in the type, all the specific instances, they're examples of the ideal element of the type. But in fact,
Yeah.
you
So,
know,
I
you
was
can
actually
have, you can
thinking-
have subtypes, you
Yeah,
can have,
well-
something can be a member of infinity number of different types. But this
Right.
is the starting vision, and
Yeah.
in some sense, you
Right.
never get away from it. You get too far away from it, people who like types will say, nah, now you're doing set theory.
Right. Well, the other answer is when you have subtypes, the way it's done is, instead of just saying A is a subset of B where every element of A belongs to B, what I have to do is I have to give you a mapping from A to B that might have the property that will send any element of A into the element of B. So in that sense, I would need this thing to get that, I would say that this is a certain mapping from A to B.
There are no
Let's say if it's one-to-one.
The ideal type theory,
Right.
simple-minded paradigm.
Right.
So this actually reminded me of, is the hierarchies?
Yes. Oh, it's exactly the same thing. Yeah.
Right, but then you can have like...
That's right.
Something can be of type like a pet,
Mm-hmm.
right?
Yeah.
And something can also be of type mammal.
Sure.
And those are like overlapping types.
Yeah.
There's
That's
no
right.
assumption here, there's no...
Sure,
typing, you're
sure.
just-
I have a question. So you talked about set theory, the example
Mhm.
of even numbers, right?
Yeah.
So if we were to do that as a subtype, basically
Yeah.
even numbers would be a subtype of integer.
That's right.
Right?
Mhm.
What happens to the odd number?
Well, so okay.
Would it return
Well, I could make...
nothing, or how does
Yeah, it wouldn't be, because you'd have a type which we can call, say, one way of doing it, I have a type called even number.
Okay.
Let's say even integer, and then a mapping that sends that into integers.
Okay.
So it would send
No,
2 as
anything
a...
that anything that returns from the function is typed by the function.
That's right.
Got it. So we have
Yeah,
number 2,
that's right.
typed by the function. Number 3,
Right.
it's not typed by the function. It's typed by A, but
Yeah,
it's not typed by
that's
A,
right.
A arrow B.
Exactly.
I get it.
That's right. So
Right.
that's right. For example, 3 would, have type maybe an odd, and in fact, first of all, so that means, first of all, 16 as an odd integer in this setup would be different as 16 than an integer. I need an explicit typecasting function to turn one in the other. So in that sense, that's how you would avoid such question. What about it? Well, even 16 as an even number explicitly wouldn't fit inside your integers, let alone and it means that then the function that maps it in would map that in and not
We have
anything
like
else.
16 is the integer, and then we have
Yeah,
another object called 16,
right,
which is A arrow B.
right.
Or even number.
That's right.
Or we can have another one that says
Yeah.
A arrow C, which would be
Right.
the number 16 itself,
That's
which
right.
it only satisfies.
That's right. So a lot of type theories about
You
explicitly.
make as many types as you need to.
That's right. You make as many as you need to, because a lot of spirit type theory is trying to keep all these things explicit and reified.
Yeah.
Whereas in set theory, you would take it for granted. Of course, the thing belongs to it. Here, you say, no, we're going to keep all that explicit,
Yeah.
just so we can make sure everything type checks. Yes.
The labeling convention on the corners of mark of type theory?
Not particularly. I mean, it probably varies from author to author. I mean,
So here
Yeah.
the subset set theory is a mapping.
yeah, that's right. That's right. Just that there, one way of putting it is, given the subset, I have a preferred mapping, right? Because I could imagine, another mapping from that subset to the thing. Whereas in type theory, we're saying it's just is nothing privileged about that one that we would call the subset. That might be a better way of putting it. All right. And then, like I said, the next is that, basic operation we have is function application. And we discuss, which just means apply a function to an argument, where, of course, the types have to match up. And then, next point I was going to make is that there are two types of type theory basic types. So one is the original one due to Church, which is called simple types. And what that means is that if I have f of x, the type of that will only depend on f, not on x. So for example, if I have a type that goes from, integers to reals, okay, for every integer give me a real, and that's all I can do. I can't make a type that, for some integers gives me a real, for some integers gives me something else. However, that can be kind of restrictive. So, Martin Luft, much around the 70s, I think, or so, said, well, let's make a more general type of type theory, which is called dependent type theory, where we allow the of x to depend on x. So this could be a type where you say, well, maybe I'll map integers into real numbers, but actually it'll be more flexible. I can map some of the integers into real numbers, and then maybe I have some other thing, geometrical figures or whatever, I'll map the others into. And I can set it up where consistently, as long as the type depends on the x as well. So I have a function whose type tells me that for certain values of x, it's one type, for others it's another.
And even the value of x then? Right?
Yes.
Not just the type.
The value, that's right. That's right. And simple type, type of x has to match, that's right. Point is, the type of x is always, in both simple, is always the same. You always have one type, x must be of that type. However, in simple type theory, type of f of x, no matter what the x is always the same. Whereas here, x has a certain type, but depending on its value, f of x may have a different type. So then we have to generalize this arrow doohickey to what's called there should be a letter pi here. I don't know why it didn't render. I must have made a typo. Sorry about that. But what this pi thing does, it says, if I tell you for each x,
Scroll right to the top of the screen.
Scroll higher.
Oh, higher. Okay, yeah, of course. There we are. Is this good? Doesn't? Well, that's fine. Okay, so what we're saying is, let's say I have an f of x where f will, for each x, give me a type. So it's a function, what they call type family, so first of all I have a type A to which my x ranges over. Then I say I have another function f that for every value of x gives me a type. So it's a function from the type A to the type of types. There is such a thing. And then I just say, then I have this constructor should be a letter pi here. Imagine I have a letter pi where the blue blob is. That thing will then tell me all functions that have the prop is a type of functions where for each f, their type is capital of f of x. Probably we can, all right. So I guess another example of that might be, like a statement. Imagine you have a, say like an if statement. If this is true, I'll give you return 1.1.0. If it's false, I'll return 2. So then the type, for false the type family where for true the value is, the type is a real float, and then for false it's an integer.
Or you can do it in the square root. If you pass it a negative number, you get back to complex. If you pass
Right.
a positive number, you get a real.
Yeah, that would probably be a more interesting example. Thank you.
Is it a pi because it's supposed to be like a product
It is.
of function?
Yes.
Function is, if you fix the type, then you just get like one of the regular.
That's right. That's right. 'Cause if you imagine your type, loosely as a set, that's exactly what it would be, right? I say for, let's say, my stupid example, what are the values? Well, I have a real number for this and an integer for that, so it's a product of reals and integers. So yes, that's why it's a pi, which didn't appear here. All right.
Is it like a template?
Well, a type is kind of a template, I guess, but. Okay. Oh, you mean template in some specific sense? Okay, then. I see. All right. Yeah. Okay. So, and now a little few words about the third foundational system, category theory. Actually, there'll be a little more about this. So this is the topic we've been spending the last 2 years on in our study group. So here, in set theory, as I said, elements and membership were fundamental. In type theory, the types or collections were fundamental and elements were rigid. In set theory, we take the point of view that actually the fundamental thing should be functions or mappings. And everything else will be defined in terms of those instead. All right. So first of all, first of all, some terminology. So they use the word morphism to mean these things because they're mappings, but they're sort of in a more abstract way. And objects are sort of going to be the analog of collections or types. And we'll see that, in fact, there actually will be interpretation where they actually will become types, and another one where they become sets. All right. But this is a sort of a third approach. So the way it works. So here's all the assumptions that go into it. So I said they're very abstract functions. So we're not thinking of them, as the concrete way where I tell you either as in set theory, given every x, here's the y that it maps to, or even in type theory as here's a rule that will compute that. We just assume they're out there, that there's this black box that has certain properties. And the properties it has are very simple. One, it's going to have a domain and codomain. So, which loosely speaking, you can imagine is what is sort of the type of input and output the thing takes. All right? Then we only make, all right? Furthermore, we say that if the things match up, so the output of one is the same type as the output of the other, then I can hook them together and compose them. Right? So if I have f that goes from b to c, g that goes from a to b, I can get the composite f of g that will go from a to c by, going through b, presumed by going to b first and then going to c, but we don't care about the details. All I know is we'll have some black box that goes from a to c. Yes?
In order to compose functions, right, in a typed environment, and
Yeah.
we're going from a domain to a range.
Yeah,
So the range of one has to be the domain of the one.
that's right. Yeah, exactly.
So it's not just completely arbitrary.
That's right.
Okay.
That's what we're
gotta be-
yeah, no, that's not arbitrary at all. But what I'm saying is it's abstract in the sense we're not saying any internals of how it's done. We're not necessarily saying that, you take these expressions and you combine them, or that. You just take your morphisms of some given things that have this operation, which observes that rule. Yeah.
Let me just to emphasize,
Yeah.
Pierre, in this setup, you cannot ask. Sometimes you can't. You can't ask for the elements of A. It doesn't necessarily have any elements.
Right.
None.
Right.
No elements.
Well,
It's just A.
Well, here's an example. For example, it may be that let's say our F's are matrices.
Right.
And your composition operation and matrix operation. That's a perfectly legitimate category.
That's right.
So it'll turn out we can define elements for it, but you may not want to see it that way.
In this case,
But there's
Yeah.
a difference between asking for the elements and determining whether an element is in there or not.
Yeah.
interesting question. I don't know.
No, no,
But even that, but I'm saying even the latter is not giving you a priori. Neither of them is giving you a priori in this setup.
Predicate or set without
Yeah.
having any function that enumerates elements of the set.
Sure. That's right.
That's what I'm getting.
But here we're saying you don't necessarily even need to tell me anything about elements either way.
No epsilon. Well,
Yeah.
that's very important.
Well, and certainly in the formulation there isn't. If there is one, it has to emerge later.
Many of the most important examples of categories,
Right.
small ones that are easy to understand, they don't have any elements. The dots, the objects don't have any elements.
Right. Well,
So we get an example.
well, I'm getting that. That's the next topic. Yes, I'm giving some example of. Well, let me just finish the one more. So the one more thing. So I said we assume that not commutes, associates. Excuse me. I'm sorry, that was a huge blunder. It's associative.
Actually, when you set it up...
Well, the diagram commutes.
The diagram commutes.
Yeah, well, that's right. But no, but the only thing
Absolutely correct.
that's right. But to emphasize the point is we don't assume anything of what these look like. All we know is from the outside. I can compose them when they match up. That composition is associative and it has an identity. And that's it. If I have any operation that has those three properties, it's a legitimate category. No, those are called groupoids. It may or may not have them. For example, we take all matrices. So if I have a 2x3 matrix and a 3x8 matrix, I can multiply and get a 2x8 matrix. So that's a perfectly good example. And you can check matrix,
And it certainly does not mean.
and in particular, they may not be invertible matrices. So, plus, furthermore, in that case, you can check, yes, associative, and there is such a thing as an identity matrix. And that's it. That forms a category. And I don't need to think of them as sets, or I need to think or anything like that.
Let me just
Yeah.
mention what the objects are. in
Yeah.
this category.
Yeah.
They're
Yeah.
numbers,
Right.
0, 1, 2, etc.
Right.
And in this setup, you can't
Right.
ask whether 3 has any elements. It doesn't. It's
Yeah.
just the number 3.
Right.
So that's well defined.
It's a weaker
Meets
restriction
these
than
axes.
group, right?
Yeah. That's right. Because a group in particular is a category that has one object and everything is invertible.
That's right. I got it.
And the identity basically says that there always will exist some kind
Yeah.
of function where like A goes to A, B goes to B.
Identity just means that if I compose it with it, I get itself back. It's a unit element.
Oh, okay.
Maybe a better word would have been unit element.
Okay. Oh, I see. In other words,
That-
a function that
that's right.
composes with itself
Right.
returns.
Right.
itself.
That's right. Or another simple example of category would be, there's one object, integers under addition. My composite, and then my unit is 0.
Is it
Yes. Yeah, monoid is just a category with one object. So categories may have more than one object. Because a monoid, I have one object, which means any two morphisms can be composed.
What is an object?
Okay, it's basically, like I said, it's basically this bookkeeping device that tells us when we can multiply things together. Think of the example of the m by n matrix. The numbers m and n were telling me when the things to be multiplied. So in the case of functions, it would be, something like a domain or a codomain.
Let me ask you this.
Yeah.
Can you think of it as like say the object 3?
Mm-hmm.
You could think of that as really something where you have a function that takes like
Right.
a domain, a null domain, let's say,
Yeah.
and translates that to 3.
Sure.
Now, the number
Oh yeah, you could think of it that
3
way.
is
That's right.
A, and then you can use another function
Sure.
that object
That's right.
and apply it to other
Yeah.
things.
Yeah, sure.
That's not what you can think of that, but that's not what it is.
Right. Well, but all I'm saying is that all I'm saying is the axioms don't assume anything further, but of course it may be the case that you could think of it that way, and that's what makes a subject interesting.
Well, those actual operations emerge later in this construction.
Right. That's right. All we assume is that we have a composition law that behaves in a certain way.
Magically means.
That's right. So I gave a few more examples, but here's a very canonical class, which are structured sets. So the point is that if you just took all sets in the classical sense, or some collection of them and all mappings between them, those would form a category because given a map from A to B and a map from B to C, I can compose it. However, more interestingly, I could say, let's say instead of my thing just being a bare set, which is just a, one of these Boole, Cantor, Russell collection of things with no it has additional structure. For example, one nice example is a graph, right? A graph, I don't just have, isolated points here. I also have edges linking them. And that's a structure because given 2 points, I can ask, are they linked by an edge or not? Furthermore, if I want to map graphs, if I map edges to edges, I can't multiply them vertices to vertices. I can't do that arbitrarily in general. Because if I have 2 vertices that are connected by an edge, that edge has to go somewhere. And its endpoints have to go there. So for example, if I had 2 points that were connected by an edge, and then I had 2 points in another graph that weren't, I couldn't map them to the other 2 points because where would that edge linking them go? So in fact, if we take our objects to be graphs, and our morphisms to be mappings between graphs that preserve the incidence relation that defines a graph, that's an example of a category.
But you can also for graphs to sets.
Of course. For example, we have the so-called forgetful map, which just says, given a graph, erase all the edges and just give me the set of vertices. And that would be a legitimate map.
That's a function.
Well, that's
Yeah.
a functor.
Yes, that's right. Functors, so just to introduce the term, all functor is a map between categories that preserves the structure of the category. So in fact, categories themselves form another example of this.
Sounds like a nice morphism.
And in fact, a graph, by the way, while we're at it, is actually just a category where you can where you have a composition operation defined on the edges. So, but that's maybe getting a little too deep. So, another common example that we'll come back to is topological space. So, topological space is one where you have points, but there's a notion of some sort of neighborhood. That these points are close by to this, these are far away, or so on. And then you would want only mappings that preserve that structure. So in particular, they don't, if you have a line, and you don't want a map that tears it into two and juggles and turns the pieces around, where these 2 points that were originally right next to each other now are on opposite sides of the thing. We want nice, smooth, gradual, nice continuous maps. Another example would be an algebraic system, where let's say a group or whatever, or a category, where you have an operation, such as, let's say multiplication of matrices. Well then if I want to map the things, I want to map them in a way that respects that operation. So for example, if I have, say, an addition operation, if I have a plus b equals c, I want a mapping f to have probably f of a plus f of b equals f of c. And as we said earlier, a category is an algebraic system, and in fact the morphisms there are called functors. So I don't want to get too deep into that, but now that it's been mentioned, it should be said. So, now let me, all right, say in what form the notion of element does reappear in a category. So as I said, it doesn't appear in the naive sense that, our objects are just sets of things. As we discussed with many examples, that doesn't make sense. But there is a generalized sense which we can apply to all categories. So first let's start with something familiar like sets where we know what an element is. And we ask, if I only describe, so the question Levere asked was, suppose I took set theory, even good old-fashioned Cantor set theory, but now I want to describe it in a point of view where I take as fundamental not the element relation, but the notion of mapping. How could I do that? Well, the answer is very simple. Just take a set with a single element. All right? Now, what is a mapping from a set with a single element to any other set? Well, it sends that single element to some element of the other set. Hence, the elements of that set, could be represented by mappings out of that thing. So maybe I have this special object like the one in that case of the category of sets. So I have a special object, the thing with one element that has a property that, mappings out of that into any other set correspond to what we think is its elements. However, if we go to other categories, that no longer holds. For example, let's go to our case of graphs. Well, as we said, a graph has sort of two things in it, the nodes and the edges. So I would actually need two special graphs to describe it. One is the graph that has just one node and no edges, because that will get mapped. As a map from that to a graph, it just sends that one thing to some vertex of that graph. But that doesn't fully describe the graph because it doesn't, I don't know where the edges are. So let me take another graph, which consists of a single link with two nodes on the end. Now, if I map that into a category, that's equivalent to, into another graph, that's equivalent to picking out an edge of that graph. So if I have these two special things, I tell you a map from this or a map from that, that completely, specifies the elements of a graph. And in that sense, we could, generalize this to an arbitrary category, which was Levere's then said. I look at these examples, Levere pretty much look at these first sets, then graphs, and notice, what I could do in general is say, well, for a category, let me consider all possible elements as starting points and view the mappings of them. So given an element A, I fix an object A in the thing. So, all right, then I say, okay, pick all the morphisms that start at A into a thing. Let me look at those, imagine those as somehow kind of elements of B. So for example, in the case of graphs, if B was a graph and A was the thing with one element, those generalized elements would be the edges. If I picked A to be the one node thing, it would be the edges. For some other category, I may have more things. So let me call this a generalized element. And this actually has, so it's not an element in the most literal sense, but it actually has some important properties. Because usually, the important properties we saw in sets of elements was that if we want to describe a function should be completely specified by where it maps the elements. Well, now if we take this notion of generalized elements, Neda showed that, a function will be completely specified by where it maps all its generalized elements. So in fact, given a category, furthermore, given an arbitrary category, if you construct, the set of all its generalized elements, and then, for each morphism, each object I tell you which ones, I give you the subset that belong to the object. For each morphism, I give you the mapping that sends generalized elements of one to the other. That actually category is going to be completely is going to be equivalent to the original category you started with. This is a very important result about it. So in that sense, all categories are sets with structure. But it doesn't mean you necessarily want to think of them that way. I mean, I could have taken the category of matrices I've given you and applied this construction to it, but that's probably not the way I would want to think of matrices.
What do you mean by equivalent?
Okay, means that inside the categories, I have an invertible map of categories between them. So it's just an isomorphism.
Is there a relation with cosets in group theory?
Well, we're not quotienting here. This is just a pure equivalence. Right? Cosets we quotient to get a smaller one. And I could certainly do it in a category. Given a category, I can certainly quotient it down in a similar way. Cosets, but yeah, well, that's not what we're doing here. Here we're just, actually the analog of this in group theory is Cayley's theorem. Okay. There was a theorem of Cayley, remember, that told you that a group is equivalent to, if you take as a set, and then you have each element is the operation function that multiplies by that element. So Yoneda is just directly generalizing Cayley's theorem to categories. So if anyone's familiar with that, that's what this is. So in that case, I'm not saying cosets, I'm just saying it's equivalent in the case of groups to permutations. You know, group is equivalent to a group of permutations, where the permutations I choose are the ones that correspond to multiplication by group elements. So yeah, no quotienting involved here. All right, so that's the third thing. Now, so that's what a category is. However, so okay, let me just, it's much easier here. So now, you know, as I said, the question is how do you actually do anything with this? I told you what the theory is. Just like in sets, I said the way, you know, we said the way we do things is given a set and a property, I can construct a set. In types, I use type constructors to make new types. So questions in category, how category theory, what is the equivalent way I make constructions to do any interesting math? And the answer is it's through what's called universal properties. So the general idea here is that if I'm given, so remember in category we didn't want to look inside things to see what elements there were and pick them out or anything like that. So what we're going to do is, so to speak, the idea is imagine I want to select my collection as a whole. So instead of saying the set of all elements that have this, but which I make by picking out elements that have the property, instead I want to say, well, let me take all the sets that have this property and pick sort of the most universal one. So the idea is that, and this actually is, so by the way, I should say that this title was borrowed from David Ellerman, for those who know him. But anyhow, the idea is that we say that, okay, given a class, so given objects of category that satisfy a property, we'll say that one of them is universal. It has a property that for any other object with that property, there must be a unique map to this one. All right, so that's kind of abstract, so let's give several examples which are actually important. So first is product. So for example, in set theory, let's have a set A and a set B, and I want to construct A cross B. What would I do? I would take an element of A, take an element of B, pair them up to form that pair. Take another element, form them, and I would in that way construct the set A cross B of all pairs. It's a set of all pairs such as the first element belongs to A, second belongs to B. Right, there it is. I take my property, I use that to pick a set. But now, in type theory, I would have had a product constructor, which tells me given this type and this type, I have a product type, which I construct by applying the pairing product construction. But in category theory, we do a totally different thing. We say, consider one property that our set should have is, well, as we know it from Lisp, pairs have cars and cooters. So I should have two functions. Whatever A plus times B is, it should have a map, projection 1, which is basically car, that gives me the first element back, and another one gives me the second element back. So now, the point is, of course, given an A and a B, there are many such, in general, sets or objects that would have two such mappings. So we say, consider all of them. If there is one that has the special property that for any other thing with that property, it maps uniquely to it, that's going to be the product. Now, why is that? Well, because if I just wanted something projects to A and B, what I might have done, on the one hand, I might have not put all my pairs in there. My C may only have some pairs, not all possible pairs of A and B. Or some pairs may have been listed twice. Now, if they were not, so the point is that if they were missing, that, whereas A times B should have each pair listed once. And why does that make it, exist and be unique? Well, if A plus B was missing something, I wouldn't necessarily be able to map any other collection of pairs into it. Right? If A plus B was missing the pair 5, 6, and C had it, I couldn't have possibly an F goes from C to A to B. Or, on the other hand, if A plus B duplicated a pair, then I could have two different mappings that send it to one duplicate or the other. But by requiring that, the thing be that there exists a unique map, we, eliminate that possibility. So the idea of this is that, we work in this way where we think of the object as, where we think of everything as a whole. Like I said, we have a morphism, we think of it as a whole, we don't look how it works, we just notice they compose. In the same way, when we want to select out objects, universally, we just say, we take them as given and say, of the ones that have this property, which one is the, maximal one that we're going to pick out. So it's a totally different way of thinking about things.
So C could be like another, like, let's say Willis is a cons, right?
Yeah.
So how do we know something's a cons? We know it because we apply car, it'll give us A.
Right.
And cooter, it'll give us B.
That's right.
Now, let's say we have some other kind of a pair
Sure.
with a different type.
Yeah.
Right? And you have new functions where
Right.
this G1 gives you the first element and G2 gives you the second element, right? In that case, you can basically say C is just like, basically whatever your construction of C is just like A times B.
That's right.
We can now make that equivalent to say, we have a function to say, okay, given me any C, I can get it. In other words, given, let's say, I have a thing called pair,
that's right.
I'll get a cons out of it.
That's right.
Okay, I can make a function.
That's right. But the point is, if I had a defective cons that, that, like I said, didn't work on all pairs or something, then I would notice that, that there would be some things for which I couldn't do this.
Take that one in the whole, basically.
That's right.
You know that for every single thing that you make, as let's say as a cons, and everything is a pair, if G1 gives you the same element A as PR1, and G2 gives you the same element as PR2, then you know, okay, there is a function that can turn any pair, or whatever you want to call it, into a cons. You can now say there's a function like that.
That's right. Okay. So the point is we consider all possible candidates and we select them out by this property that this one should be universal. That the real, whatever I can use the real cons should mean that any such function can be uniquely expressed in terms of it.
Okay. But in this construction, you're technically not supposed to talk about elements, right?
Well, I'm using the word elements just to give an example of set to illustrate.
Correct.
But sure, all you're saying is that,
Could you just say,
these are just morphism.
F composed PR2 equals G2 F composed PR1.
That's right. That's all you assume, yes.
That's what we're really doing.
Exactly. That's right, exactly. If we're using an example like the matrices, that's what it would be. Because we have a product there too, but obviously the element doesn't make sense. I was just using that for sake of illustration. Absolutely. All right, so then next I'll just mention, since it's ubiquitous, it's a generalization called a pullback. So the idea is, instead of being given A and B, suppose I was also given two maps H or morphisms to C. So the idea is, the intuition here is I don't just want all pairs. I want pairs such that H of the first thing equals K of the second thing. So it's kind of a restricted version of it, where I don't just want, the whole product, I want this. And that, which appears all the time in actual practice, more often than that. So sort of, you could imagine there's a sub thing of that I don't have to, but, so it's called the pullback. So it's, again, the definition works the same way that I assume for any other D that has this so what I want to assume is that in addition to, these projections going to A and C, I want to say if I project to A, then use H, that should be the same as projecting to B and then using K. And I'm saying for any D that has that same property, that D should uniquely map in.
There is a G2.
Right.
That goes from D to.
That's right.
I guess, what is that, A times CB?
Yeah, A times B, I put a sub C just to distinguish it from the regular product.
Oh, okay, got it.
Saying that it's got this extra condition involving C.
I see.
That's like the when you call it a fiber product, it's like
it's called, absolutely.
Over C, like
it can be, yes, that's another terminology for it. Absolutely, and that's, when I get to geometry, that's how you can interpret it. Because basically one way, I'll say more of that when I get to fibers and geometry. But yes, this is called a fiber product and it's used all over geometry.
So what this means is that basically you have something that's like kind of like a pair. With two elements of which are related somehow.
That's right. You're only allowed to pair related things. Yes, exactly. That's exactly right. We have a relation, we can only pair things that are related, which is more general than that thing which would be sort of a trivial relation. So that's and then I'll have two more examples which are important for what we're going to do. So the next one is, is actually, we're going to meet another friend from Lisp, Mr. Eval. So the idea is that now let's say we know something about what a pair is. So let me use it. I'm going to talk as if sets, even though it's more general. So the idea is that suppose I have something goes from, so I is, I'm imagining some kind of an index object or index thing. And I'm saying that if I have a map, from I cross A to B, that's the same as having a map for every for everything in I from A to B. This is basically currying, right? If I have a function of two variables, if I fill one slot, I have a function, but I have a family of them because for everything I can fill it in. So this is how currying is going to appear in category theory. So we have such a function, I can think of it that way. So what I want to do, I want a universal thing for that. So in other words, if I give you A and B, I can give you some two-place function that gives me, some functions from A to B, but it may duplicate them. But I want one that gives me one uniquely. And we know what that is in Lisp. It's called eval. Right? That, here I'm going to say, okay, I should have actually, it's okay, I should have the order the other way. That what I'm saying is that now I have, so the idea is that for any index thing I, so B to the A is meant to be some of the object of all the, all the functions from A to B. The idea is that then if or some representation of them. Yeah. So then, imagine B to A as being all possible quoted things. Right? Then I have eval, which, actually in Lisp it would really be more apply. That given A, I could apply, this quoted thing to it. Yeah. I mean, for some categorists call it eval, even though it's really apply in Lisp. That's just a little mismatch between subjects, but. So if such a thing exists, they call it the exponential. And okay. So the idea is that you have this object which corresponds somehow to all maps, all morphisms from A to B in there. So that we can apply them, you can imagine, yeah. Please say. Yeah, please do.
Have no
yeah, don't have, that's right. Or any of the, that's right. That's right. That's right, but the ones we're going to study do. Yes, all these constructions do not need to exist in an arbitrary category.
None of those constructions.
You
need not have products, pullbacks, anything.
Right. That's right. If you don't have any, there's not much you can do, so you assume some such construction exists, but which ones will depend on your category. And the first thing when you're given a category, you need to determine which constructions I can do. Yeah. But this is, something that lets you do it. Now, this also introduces a notion of so-called internal versus external. Because the way I define categories, I told you I have a collection of morphisms. So I can, I can certainly say, given an object A and a B, give me the set of all morphisms that go from A to B. Like, for example, given 2 and 3, I can give you the set of all 2 by 3 matrices. But what this is saying is now there's an actual object in the category that behaves something like that set. If you think of its generalized elements, they will correspond to the elements of that actual set. And this is what people call an internal construction in that sense. That there's externally, I have the set of all morphisms from A to B, but here's an object that behaves like that set. And in ways that can be made precise, and it can be used as a substitute for that. So, okay, finally, I'm just going to do one more construction like this, and I'll give you the flavor of this. So here I let me say what happens if I have a map. Well, first I should say a monomorphism simply means a monomorphism that's basically, you could say, one-to-one on generalized elements. It's another definition, but it's basically something like an inclusion. Remember we had the discussion a few minutes ago about, what happens to inclusion in types. I said, well, they're a one-to-one function, so this is one. Now, if you think about it, if I have a one-to-one function or a subset of an index thing cross A, that corresponds to a family of subsets. So this is sort of a opposite notion to currying, in the sense that I pick, subset of, let's say S is a subset, but I pick only the ones that have a certain value of I. And if you visualize that, if you think about it for a minute, that would correspond to a family of subsets. So now, what would a universal thing here be? It would be well, here's a diagram that, I would have, I'm calling it P of A, for reasons we'll see. It should be some index set that has a property that, any way I could index sub things of A, there's uniquely one in here. Now, if we were dealing with set theory, we know what that is. It's a set of all subsets, so-called power set. And again, some categories have those also. And in fact, the ones we'll be studying and using for this do. So it's called a power object. So now I put in the comment Jay just made that none of these things in an arbitrary category need exist. But in the interesting one, but the ones that category theory study typically have them because that's what allows you to do anything interesting with your category other than just write it down. So the particular, some of the terminology is, if you have a pullback, okay, something called terminal object I discussed, and which is another one of these, an exponential, that's called a Cartesian closed category. And we'll be using those in a minute for type theory. Then if in addition to having, the pullbacks and the exponentials, it also has power objects, it's called a topos. So topos on the first slide. And by the way, the reason it's called topos is that these things first arose in the study of topology. So Grothendieck recognized that, when you look at topology, actually most of it can be formulated in terms of a property of a category of certain categories, which he called topoi. And so that's what I meant to the second T in hot. So it's categories that have these properties. But why? So now the question comes, well, why are they relevant? It looks like I have two totally disjoint things when I told you about types and categories. On the one hand, I had this theory where everything has its type, and I have lambda terms, and then this other thing where I have, instead of explicit lambdas and terms, I have just these abstract functions that somehow I can compose, even though I don't know what they are. What do these things have in common? What do they even have to, and even more, what do they have to do with the foundations of mathematics? And that's what I will be discussing in the rest of the talk. So, in the part. So first, let me just go back to logic. So now we'll go back to, well, actually maybe not quite George Boole, maybe Huntington, but classical logic. So if we have classical logic, what do we do if we have a proposition there? We simply say a proposition is going to be either true or false. Now I said it's gotten blown out of the water in the 20th century. For example, Lukashevich said, well, maybe instead of true or false, we may have other truth values, and then we have other logics that don't have truth values at all, and so on. But certainly in 19th century logic, that's how it was done. Yeah.
So when you start talking about truth, you're very subtly introducing the notion of semantics?
Yeah. Yeah, you could, sure. That's right, very simple semantic, but yes. Yeah, it's a semantic approach. Given a proposition, it has a meaning, which in this case will be it's true or false.
It gets very
Yeah. Yeah, that's right. But this is the trivial 19th century case, which is why I want to start with the trivial 19th century case. So, and then the point is, now if I have a more complicated thing, how do I determine it? Well, I have truth tables that tell me if I have P and Q. If I know what P is, I know what Q is. I look up the truth table for and I find out the value for P or Q. Or if I have, for all x P of x, well, I go to every x. If it's true for every x, yes, the statement for all x P of x is true. If I can find a counterexample where P of certain x is false, then the statement all x P of x is false.
So you can't have truth tables for all x, right?
Not strictly, yeah. That we can use the notion of truth value to define it, right? That if I have a model, the quantified statement is true in a model if for every possible value of x, I must get true. And if I find and if I can show you a value for it's false, then by contradiction I've proven that statement is false. Yes. So this is, that's right. So it's not just truth, but in the case of just purely propositional logic, it is just truth tables.
So one thing that always confused me about Hot when I was reading this, was this idea of not being the same thing.
Sure.
So doesn't that violate Boolean?
Absolutely.
Okay.
But see, that's an example of logic that doesn't have truth values. And we're going to get to an interpretation that allows that next. Okay. And that's exactly the reason for this. Okay. So so that's exactly as you said. Now we know that's like you said. We know that doesn't always hold. Right. And in fact, one of the so one
It holds in Boolean.
yeah, that's right. But once you get beyond Boole, once you get to, once Lukashevitz and Gödel come along, everything changes. So, in particular, Brouwer, Heidi, and Kolmogorov were interested in thinking of math constructively. So the idea was, problem with this truth value is it's sort of, might sound too omniscient, right? That, given this thing is true or false. But the question is, how do I know it's true or false? In mathematics, I'll probably have to actually do some computation to find out. So instead of, sort of sweeping all that under the rug, they wanted to keep that, keep that in view and say, well, let's formulate logic in a way where I don't just assume there's some procedure by which I determine that something is true or false, but I actually keep in mind the fact that there is, something about what that procedure is in my formulation. So their idea was to say, well, instead of just, saying, given a statement, just, telling me it's true or it's false, what I'm going to do instead give you as my semantics is, some sort of proof certificate or witness to it. So, example, you probably all heard of proof certificates where, let's say, when people do cryptography with numbers, right? They may assert that this number is prime. And then they give you a certificate, which is, something that I can compute to check that, yes, this number really is prime. They say, you do these computations, reduce it modulo this, you'll get that value, which we know by a certain theorem makes it there. So the idea is that this thing we call proof certificate or witness should be something like a constructive procedure I can use to verify it. So don't just tell me anything is true, tell me how to see that it's true. Or something that, I would accept as a token that it's true. And so the idea was that what I assign to it then is so when I evaluate my statement, instead of giving either true or false, what I should produce is a collection of these certificates. If it's false, it doesn't have any possible certificate. If it's true, it has one or more. All right. So instead of truth values, they want to use this more explicit thing. So then the question is, well, what do we do next with logic? How do we reformulate logic? So with true or false, it was very simple. I gave you a truth table that told you, if I have a statement that has a connective, how to evaluate the truth value from the truth values. Yes?
So is it kind of like, if it's false, you cannot provide an explanation?
That's right.
It's true.
Yeah.
If it's true, you can provide an explanation.
That's right.
And would these be composed together so you could find, for example, if you had a complicated statement,
yeah,
it would explain it because these other ones were true, and
that's right, and that's exactly what
Sorry.
That's exactly what this is getting to. That's right, which is exactly the point. So now we're just saying how it does that. So now let's be a little more explicit about what you say if you have a complicated statement. First of all, if the statement is of the form P and Q, then what do I need? I need to provide a certificate for P, and I need to provide a certificate for Q. Now, if it's P or Q, then what I should tell you is which one it is, and a certificate for that one. So for example, I might tell you it's P, and here's why it's P. And that would be a certificate for the proof of P or Q. Then if I have if P then Q, what I can do is, or P implies Q, what certificate should be is a function that, given a certificate for P, will produce me a certificate for Q. So and this is the way that, given a complex stimuli said, this is being explicit how you would go about taking the certificates or simple ones to produce a certificate for the full thing. Yes?
And that preserves the semantics that if P is unwitnessable, the function is still true in a sense?
Right. That's right. So that's right.
It's still a function, you just never can...
Right. Well, the point is, okay, it's kind of a trivial fact. It's kind of this edge case, right, that there exists, you can't have functions out of the empty set. Because if you think strictly about the definition of function, there's exactly one function out of the empty set.
But void, a function out of not the empty set, but the non-existent.
Well, that's right. Non-existent means empty set of witnesses. So if you think there's a little edge case or quirk when you're dealing with functions that actually, because a function is defined, right, for every x in the thing, I must give you a y. But if I put empty set, then the empty set is a function from the empty set Because for every x in the empty set, yes, I have something. Because the x's don't exist. So by that quirky edge case, this actually works.
Is there a logic where if something's false, it doesn't have any possible implication?
Jay would do. Yeah, I mean, because usually I think that,
If you don't know the answer, I was just...
Yeah, I'm not offhand, but there probably is one, but...
It's troubling me how implication was like a false implication.
Well, I mean, one thing that's like what you have are relevance logics, where you at least need the, premise to be relevant to the conclusion, and something along those lines may have that property. Yes?
Some of us have never forgotten our first reaction to serial implication. And the answer is, we were right. But the other side is also right. There's a lot to be said.
Yeah.
But if you aren't shocked when you first hear about material implication, you have no logical sense whatsoever.
Right. And the same thing will then hold again when we get to quantum logic.
Yeah, I don't know what to say.
All right, well, but that's a totally different talk, so back to...
I had a different...
You left Jay speechless. Congratulations.
Wrong. I said to myself, what are they talking about?
Okay, all right.
What's the question?
Right.
I'm sorry, what's the question?
Yeah.
Is there a logic where
Yeah.
you can have a contradiction and not have something bad happen? Is that the question?
Well, he was saying about, he was more objective to the fact that, from false I could conclude true things.
Because from the
Right.
contradiction, which
I guess,
involves
yeah,
the
that's right.
explosion
Right,
thing.
that's right. So I said one place I know that they limit that is relevance logics.
So Graham Priest has
Okay.
error-consistent logic.
Well, that too.
Yeah.
That's another. Yeah, that's right. That's another class of logics where this
Just relevant.
hold. You're right. Yeah. So those are logics where, given an inconsistency, you can't just prove anything. It must be related to relevance logic in the sense that you can only prove relevant things from it. So there's that classical example of Hardy's. If I'm the king of England, then 5 equals 6.
So when you start off with something that's false and conclude something true,
Right.
I'm pretty sure that's called irrational reasoning.
Yeah, well, that's what the paraconsistent things allow. So I think part of the idea is if you have some relevance, you can say, from something having to do with, people, I shouldn't be able to conclude something about numbers. And it's kind of a way of keeping your system safe. That if I have a conclusion here, it doesn't spoil everything automatically.
Unless you wrote
Yeah, well, then all bets are off. But right. So all right, that's a little more fancy logic than the word assigned today, but it's logic. And then also, the three of them gave interpretations for quantifiers. Although, as we'll see, to be really constructive, you may not want to use the for all and exist quantifiers. But if you do, you can do it in the obvious way of saying, well, if I want it for all, I have to show you for something that for everything gives me a value, and etc. And then finally, as I said, the last point was the one we were discussing about false here being represented by some kind of an empty set type thing. In other words, I can have no witnesses to the statement. So in this, they usually write that thing as this bottom symbol, where we simply say that bottom has no witnesses. So it's all right. So that's that. So now, so this was, like I said, a general way of if you want to think constructively, it's kind of a program. This is how you should think of proof certificates of truth values, and this is what we're going to do to evaluate complex statements. However, what this doesn't tell me, so in particular, is that if I have this function, it begs the question of, well, what do you mean by a function? Because for the last half hour or whatever, I was discussing to you different notions of function and saying, it could be the old Euler thing, anything goes, or it could be, a thing where I need a specific formula, or it could be this abstract version of category theory. So what we're next going to do is to say, well, let's take this idea, but now see what happens if we take, one or these other of these specific notion of function, what this gives us. And particularly being constructivist, probably you would want something like the definition, D'Alembert thing, where I need a specific formula to give me a function, not just any arbitrary mapping of values All right. So.
How do you combine witnesses when some are pairs and some are functions?
Okay, when some are pairs and some are, let's say, so what you might have is, let's say I have a statement A and B implies C. So then that function should be a function from pairs to single thing. See, a function has to be pairs, right? Obviously has to, to be specific, to work, must have the range being whatever A is and whatever B is. And some of those may be pairs. So if I have a statement of form A and B implies C, then I want a function that takes pairs of witnesses and gives me a single witness. Or if I A implies B and C, then I'd want a pair of function that gives me pairs as a result. Yeah, so it obviously has to be consistent with whatever it is. And in fact, now we are going to bring in the type theory right here, where we'll make that explicit. So what right, yeah, exactly. We're going to use that's right, our functions will all be given explicitly by lambdas, and we will want to have types. Exactly for the reason that was just mentioned here. Some of our witnesses might be pairs or something, then I obviously need a type of pairs so that everything is consistent. So this is what Curry and Howard did. So as I said, this is the same Curry who gave us lambda calculus. So his idea was, well, let's take this, basically what happens if we, interpret our functions in terms of lambda calculus, or strictly type lambda calculus, what happens to this notion of logic? All right, so following a suggestion by Jay, I am going to just restrict to the case of one connective, which is implication. Yes. Uh-oh.
Allow me. I always interrupt, but
yeah. Well, this is related to his Lisp New York talk, so.
Not always purely pedantically. This has annoyed me for years. You put a parenthesis here. That's all.
Yes.
Just
Right. Well, okay. I don't want to start.
Completely serious.
Yeah.
This is completely serious. It's a very deep question.
Well, you're right. Maybe I'll leave. Okay, you're right. For Lisp, I should leave it in. For Haskell, maybe I can leave it out.
Well, that's because at least they often say something. It's right associative. Now,
Yes.
Your notation might be
Yes.
right associative,
Yeah.
not the operator.
Well, and how do I get an operator without a notation?
I mean, this is one of the most incredible things. Computer programming, which is based upon tight logic, tighter than any logician has ever seen, they go crazy when they talk about it. Is it a function or an operator? Are you crazy? That's a wrongly typed question.
All right. All right.
Wow.
Okay. So, right. So as I said, so yes, please, please imagine parentheses, extra parentheses. This is Lisp. I'm sorry I didn't put enough parentheses in, but all right, we'll go on.
Parentheses are, I've already had them in my mind. I've already projected them in my mind.
Okay.
I already see them all there.
All right. Well, anyhow.
Just in a different font.
But that's right.
Invisible font.
Well, it's like the pie that disappeared from your slide. Okay, so now, as I said, we want to remember, this constructive proposal that Kolmogorov had, you would say, okay, if, implication should be given by a function. So as we said, now we're going to say, well, what happens if we take those functions to actually be given by lambda terms, and type lambda terms at that? All right, so what we can imagine is that for a proposition, I'm going to associate a type to it, because it has witnesses, and we just discussed, some of the witnesses may look different. For one proposition, the witnesses might be pairs. For another proposition, the witness, if it's this prime number thing, might be an integer. For another thing, it might be a geometric construction, or it might be a piece of computer code. So to each proposition, I'm going to imagine there's a type, and then obviously if I have P implies Q, then that should be a function of the type that turns where type P is, goes from type of P to the type of Q. And we'll want them to be explicit functions represented in lambda calculus. Then one notices something very interesting when one starts going down this path. So first of all, if you look at axioms for propositional logic, Lukashevich wrote some down, and if you just look at the part that involves implication, for intuitionistic, so-called intuitionistic propositional calculus. I don't want to say that, just a technicality to make this right. But the point is, for propositions, if I take these two axioms that I drew here, Q implies P, so that's the arbitrary antecedent. It just says, given a statement, I say if I have P, then I have if Q, then P for any Q. All right. Then this one is kind of a distributive thing. If P, then Q, then R, I can distribute P over it, or if P, then Q, and if P, then R. All right? So these are two tautologies, and furthermore, you can show that any tautology can be derived from these by repeating them. Yeah.
So is P, QP the first one?
Yeah.
Kind of like lambda abstraction almost?
We're going to relate it to that. We're going to relate to lambdas. Yeah, well, that's what we're getting.
I don't understand the second one.
Okay, so the second one,
okay.
I mean, yeah, if you're not sure, you can always write down a truth table and check that's correct, but it's basically a kind of a distribution. I mean, what am I saying? That if I have a premise P, if I assume P, one way of thinking is this one. If I can assume P, I can prove that Q implies R. Then what the conclusion says, then if I knew P implies Q, then I could conclude P implies R. So a way of thinking about it is, if I have a premise, if I first show that Q implies R, so I can hide if assuming P, I can prove it.
Okay.
Then not assuming P, I could say P implies Q would imply Q implies R. That's usually the way this gets used. I make an assumption. Under the assumption, I prove something. And then the question is, well, how would I rephrase that in an environment where I don't explicitly have that as an implicit assumption? I make it explicit. Right? Because P is my implicit thing. So that may be a way that's the way I think about this one. I mean, tautology. And the point is that actually, if you just use these two things, you can actually prove any tautology from them. But now there's an interesting. Now we go in the other direction. So now I'm going to bring something in from left field. So this actually comes from Dustin's talk at Lisp, New York. So if we're doing lambda calculus, a combinator just means we can have lambda terms that don't have any free variables or built-ins. Those are technically called combinators. So here's an example of two of them, right? The only thing symbols that appear x, y, z, but all of those are attached to a lambda. So now, an interesting thing is that Schoenfinkel showed that if I take any such lambda term, I can get it by a repeated application of these two. So what is k? It's the constant thing. It just tells me, it gives me something that's constantly x. Constantly y, because there's no y in here. So it just gives me a constant function. K of 1 is the thing that's 1 for no matter what x is, or y. And then S is, okay, it's a little more complicated, but basically you can think of it as a form of application. You apply one thing to the other. And it actually depends on a parameter, extra parameter z there, but so I have x of z it's the same as x of z of y of z. So the idea is, okay, so anything in lambda calculus, I think Dustin actually, discussed this, and I won't go through it, but you probably see it somewhere. And a very nice place for this is, by the way, the unlambda programming language, which I learned about through Foray. Yeah. Where someone actually write something that only uses this.
So these are the operators from the ski calculus?
Yes, that's right. Except the no I, because that can be expressed in terms of them. Yeah. That's exactly those.
K is really easy, but isn't S supposed to be kind of like substitution?
Yeah, you can. Yeah, it has that's right. It has substitution and application both in it. So the idea is, you could have written a combinator that just substitutes and one that just applies. So then you'd have, K and two word combinators. But Schoenfield notes if you wrap them up together inside this way, where yes, I substitute the value of z, then I apply, I can recover both substitution and application from that.
Pretty confusing.
Yeah. Yeah, since get kind of messy. It's probably best left to a Lisp interpreter to check that they really work, but You can write the right combination, and yes, it will reduce to both of them. So it does those two. So in that sense, you have all the three basic, if you have, constant functions, application, substitution, that's all any lambda term could possibly do. And indeed, you can show, check that, yes, this will be right in these. But now, here's the interesting observation. If we ask what the types of these are. Well, let's say if, okay, so here, let's see, the constant term, the point is, if I give you something of type P, something that's constantly P, then no matter what arbitrary type Q I have, it'll give me something back of type P, just the P that it's constant on. So that's a type of this. And this one with the, substitution application a little more messier. So, but it works out to be the same as the type of this particular proposition. And if you think about what the proposition do, that's not completely accidental, right? Because the first one in logic meant, I'm supposed to have an arbitrary antecedent. So the thing is constant. It doesn't depend on Q, which is what the constant function does. And yes, if we make that, if we think the interpretation of, that constructively I should be having some operation on witnesses, the obvious thing to do to implement this is say, well, I just throw the witness Q out. The judge bangs his gavel, witness is dismissed, and we have only a constant P. And likewise, if if like Curry and Howard, you spend enough time staring at this one, you could convince yourself that the interpretation of this S does agree with what this thing should be doing about taking a proposition you assumed and making it explicit.
Wait, so shouldn't the variables in K be the other order, like lambda x?
Maybe it's possible. Yeah, it's possible I have a typo. I'll double check that before I put up the published note. Yeah, it's entirely possible. I juggled a few of them, so I won't vouch for it. I'll double check with a textbook before I put it online. All right. So the point is that because of this, what Curry and Howard concluded was the following interesting fact, that now, if you want to check whether a statement is a tautology, interpret it as the type of a possible lambda term. If there exists a lambda term, then it's a true statement. Otherwise, it's not, or it's not a provable statement at any rate. Yeah.
Lambda term of the type.
That's right. Yes, that's right.
Different theory.
Yes. Right, that's right. Yeah, so we want to use Arthur's version of Lisp for this, which has the types in it. So yes, in a type lambda calculus, we find such a term. Now, however, so the idea being that term, works as and what the interpretation of that lambda term would be, that's the lambda term that if I apply it to witnesses for P, Q, and R, gives me the witness for the full statement. So the point is now, instead of just saying there's some function that did it, we're more explicit. It's a lambda term, and we can tell you which lambda term by using these basic combinators to correspond to the axioms. So that's what the whole point of Curry and Howard. And there's an interesting point here. Now, because remember what I said was that, there need not be just one witness. And this is another point that Jay has been making at many restaurants after our talks over the past 4 years.
Haskell is alive.
Well, I only figured it out.
Well, is it fine? Let's say I have the simple statement, P implies P implies P implies P. Right. Now, what would that mean as a type? Well, P implies P would be a type of functions from P to P, or witnesses of P to witnesses of P. So what this is saying is, given a witness of P, a function of type P to P, I'll put another function of type P to P. Now there's an obvious way to do it. Give me the same thing I put in. But there's another thing I could do. I could compose a thing with itself. And that gives me another one. And that would also be a witness to that tautology. But those are completely different. Clearly, giving me the function and the function composed in general are not the same. Right? If the first function was squaring, then the thing composed with itself would be raising the fourth power. They are not the same. So this is an example where you have proofs or witnesses that are not only more than one, but they're completely different and not equal in any sense of the term.
But
yeah.
A implies A, like an obvious tautology?
Yeah, but this is the tautology A implies A implies A implies A.
Which is the same thing. Let's just call A implies A.
Yeah, well, it's a case of that, that's right. But because it, yeah.
A implies A.
Yeah.
Implies.
Right, sure. Yeah.
And that's how you determine if two functions are equal, if it satisfies that property.
No.
What we're saying is that this property, you said it was a witness to that tautology.
Right?
But what we're saying is that in this case, we find out that there are lambda terms in there which are completely different. Because the point was, in classical logic, all we had was this thing called true.
Right.
Now here we're saying instead of true, we should have witnesses, which in this case become functions or lambda terms. And so instead of a single true, we have things could be true in totally different ways. That's the new twist here.
So we have a classification of
Right.
in the intuitionistic propositional calculus with only one connected arrow.
Yeah.
Completely classified proofs.
Yeah.
Sometimes two proofs look different, but you look at it a little bit, you can wiggle them around, and you see, oh, they're really the same proof. Like the trivial rewriting. Curry-Howard proposition.
Of what?
This is our type.
What do you mean by classification?
Well, that was the example. I'm sorry, I didn't write it down. Well, let me see. Okay, let me write it down. Oh, I can do it.
Correspond to lambda terms of that type.
Well, I'm saying this. See if I can type here.
But then there's this further theorem.
So by classify, you do mean sign type?
No, I mean classify.
What does that mean?
Suppose you have two.
Oh, this won't take too long, but
Sometimes you look at them and you realize they're really the same proof. This is a formalization of that phenomenon. It's perfectly precise.
Right.
And you're willing to believe it.
Well, see,
theorems, which I think
well, here's one way of saying what Pierre was saying. This is a case of one way of proving this is to say this is a case of tautology P implies P. What we're saying is it has other proofs that don't look like that at all. So point is, we're not just showing that this is actually true, we're trying to say how many different ways we can show that this particular statement is true. So that was this, and this is also, and this feature that, you may have different proofs of something that are different is called proof relevance.
Okay. Do we have any examples for that?
Yes, this is the example. Well, okay, so what if we think this is a type, this should be something that takes a function from A to A and returns what? This is a proposition, right? It's just a simple proposition that A implies A implies A implies A.
It's actually a drawing that we are interpreting as proposition.
That's right, we're interpreting a proposition. We're trying to say, how do I prove that this is true? It's a very simple thing to prove, but if we use this setup of Curry and Howard, I'm supposed to find a function that, does this. So one function that does this would be the identity function. So let's say if x is a function from A to A, then I put, x, the identity, yes, I get a function to A, another function from A to A. But I could have also picked I'm getting faster at this.
K1, for example, right? Y-X.
Well, yeah, I guess, well, or I'm just going to pick this one here, right? So the point is, if x is a function from A to A, then, sorry, not this, I meant x composed with x, excuse me. Or there's an eraser here somewhere. So if I take x composed with x, that's also going to be a function from A to A. But the point is, in general, x composed with x looks nothing like x. So both of these are witnesses to the fact that this is a correct proposition, or proofs of it, proofs that this is a tautology, but these don't look at all like each other. There's no way I could turn this to that in general. if F is the identity, yeah, F composed with F is F, but if F is squaring or almost any non-trivial function, X composed with X is not going to be the same as X.
Yeah.
That's the point here. Okay. So that was, so that's, for now, my survey of this, Curry-Howard, just that we're, okay, good, looking at it, okay. Sorry? Yes. Yeah, when we get to geometric interpretation, I think that will come out. Sure. Yeah. In fact, after I do the next thing, I will, sure. Yeah, it should be. All right, so next thing is, now we're going to do is, so what I did here was basically take this old idea of the way I described was, if we start with the idea of Kolmogorov and interpret it with the notion of function in terms of type theory. So now I said, so now what I'm going to do in the next section is say, well, what if we took that same notion, but now interpret things in terms of category theory instead of type theory. So instead of types, we're going to have objects, and instead of lambda terms, we're going to have morphisms as our functions. What happens? All right, well, that's what Lambek and Scott did. And so I'll just give an outline, give a rough outline. At this point, things get a little sketchier. So first of all, first I remind you that by Cartesian closed category, I meant a category in which we had products and these internal exponentials. So that's, remember, for any two objects A and B, the product A times B was defined, and A to the B, the object A to the B of mappings from A to B was also defined. So we want a category to have those two properties. And what I'm claiming is that if we have categories like that, those actually have a correspondence to simply type lambda calculus. And here's how we'll do it. So first we'll notice some analogies. Like I said, a type is something like an object. They're both, some vague, loosely they correspond to the same general notion of a collection, as I said. All right? Then a product, well, we have products in both. I just told you a Cartesian category is defined as one with a product. And in type theory, we had a type former which could form products. All right? And like I said, corresponding to the type of mappings from type A to type B, we had this object which somehow classified the morphisms from A to B. So we have a correspondence at that level.
Yeah.
All right? And now, let's see if we can extend this to what we would do with terms. So the question is, what I want to do is I want to say, okay, now I'm given a lambda calculus, I'm given a Cartesian category. I want to interpret the terms of that lambda calculus as some morphisms in that category. Because both these are supposed to correspond to the notion of function. Now we want to be explicit about it. So here's how you can do it. So like I said, okay, so a term will correspond morphism. Now, let's say I have a ith variable. To imagine my expression has a bunch of variables in it, x1 to x5 or whatever, and I want to say the term x2. What is that? Well, if I have my 5 x's, I can get that by applying the projection thing that projects out the second term, which is exactly what I have, which is exactly, if you remember how we defined the product, was by saying it had projections. All right? Then, going the other way around, if I have a pair of terms, I can interpret that as saying, well, in my category, I take the product of the morphisms corresponding to them. So I mean, I defined you product for objects in a category. It's relatively straightforward to extend that definition to product of morphisms. So we use that. Then finally, okay, this was, all right. Yeah, okay, I'm saying if my term happens to be a product, I take the ith subterm. This should have been saying projection on tau. I typed projection wrong, so it didn't appear here. Sorry about that again. Then if I have term 1 applied to term 2, what I can do is, in my category, remember, I had this, the way I defined the A to B worked, I had this eval, which given A to the B, which was the things from it, was really more an apply type thing. Yeah.
Is the val well defined?
Yeah. Okay. Yeah. That's right. Although it's really, you should probably read it as apply.
Okay.
Because, yes, category theory is right eval, but it's really what we call apply. So you say, you know, okay, if I give you the pair of the two terms and then I applied the first term to the second, that's the same as term 1 of term 2. All right?
The vertical bar, tau 1, tau 2, or
yeah, I should have probably written tau 1 of tau 2 with parentheses.
I thought there was some type rank or something.
Some, yeah, different, well, both conventions get used, I guess. I mean, a lot of people write lambda calculus tend to write the bar, but...
Are you saying that is a sum type?
No, all I'm saying is, no. Tau 1, all this means is, this means tau 1 per open parentheses, tau 2 close parentheses. It means the same thing.
Right.
It's just that lambda theorists since Curry have written it as a bar, and I just copied it from a book. I know I should.
Right.
Oh, they use a plus. Okay, well.
No, they use that in place of plus.
In place of a plus, okay. Even though they named it after the guy who used the bar for it. So.
We'll figure that out later.
They don't want to be ML.
Yep. Well, that would do it. Okay, yes. So, right. So anyhow, there we go. So that's how we can, you know, inside our Cartesian category, we have the supply type operation, so we can present that function. And finally, what about lambda itself? Well, what does lambda do? It adds an extra, makes y an extra variable. That shows up. So all I have to do is say, you know, interpret that inside my category. I want to interpret the thing in terms of having variables x and y, not just x.
The universal there?
Well, yeah, the variables are sort of implicit because I have morphisms, right? They, you know, a morphism goes with some domain to it. So the variables here are associated with the domain of that.
We haven't really defined what variables are.
Yeah, well, I mean, they're pretty well defined in terms of on the lambda calculus side.
Right.
So what we're saying is that corresponding, so what I meant is that given a variable x is going to go over some domain. So by the symbol tau sub x, I'm meaning I have a morphism whose domain is going to be whatever object I associate to a variable x. So if I have a lambda term y, now I've introduced a new variable y. So this lambda term, in addition to whatever x is already in tau, will also vary over y. So that's the meaning of this notation. That's right. So we don't have variables in categories. What I mean is that to each variable we associate some object that can be the domain of our morphism. And that's what this notation is. It's fine. And by the way, got this from, never mind. Now, anyhow, so and now we go to a next step. So this is just saying, you know, if I had lambda calculus, some type lambda calculus, and some Cartesian category, here's how I could interpret it, meaning, you know, given a lambda term, I could produce a morphism in that category. Did it, but there was, you know, but now I'm going to do but now one can be more specific and say, given the lambda calculus, I can actually construct a specific category associated to it, which is somehow, you know, universal here, in a sense I won't try to get into now. So the way we're going to do it is to say that in our type lambda calculus, again, I'll associate the objects of the category will be, you know, types as they were before, the types of the thing. But now my morphism I'll have, in this case, instead of just picking any old category, I'm going to say the morphisms are actually correspond to a pair where x is a variable in the lambda calculus and tau is a term that involves x. So it might be, you know, x and x of x or something like that. All right? And then particulars of identity, I'll pick the thing where the term is just x. And my notion of composition will be basically substitution. So that if I have a term tau 1 that depends on x1 and a tau 2 that depends on x2, as my composition, I take, well, substitute, you know, into tau 2, I should substitute tau 1 for the variable x2. So it's sort of the obvious thing if you had terms and you wanted to, you know, what would be the notion of composition there? It's substitution. So, all right, and the point is that if we do this, we get a closed Cartesian category, and we can check that, you know, that this, in the sense we had before, sorry, this thing will give us, what did I call it? I just want to get, that'll give us an this gives us an interpretation of that lambda calculus in terms of that closed category. So that, so in that sense, we have the correspondence between the categories and the lambda calculus. Where now basically as we construct this category where the morphisms were a substitution and the types were objects. Or that was what Lambek and Scott did, and then verified that it all works. And so taking that, and then, all right, so then, and of course this could then be associated to our logic, because what it means, we could now have an interpretation where, we say that, okay, if I take implies, instead of being a lambda term, I could interpret it as a morphism in some Cartesian category. And the point is that using this construction, I take Cartesian categories, they don't look at all like lambda calculus, but if I make this association where composition corresponds to substitution, I can check that actually given any Cartesian category, I can rewrite it as a type lambda calculus and vice versa.
So now you're starting to get into the realm of why the equivalence between
yes.
And how
yeah,
to unify.
That's right. So in fact, this is building up that table in chapter 1.
Yeah, right. Which I actually like a lot.
So what I'm trying to do now is give the rationale for that. Right. How do you do that? Right. So first, they had a column which was basically classical set theory. They had type theory. That was what I did with the previous section. And now I'm doing the section, what would be categories. I don't know if they quite have that one in their table, but.
Can I ask you one question?
Yeah.
Too? And feel free to take this offline.
Sure.
And Jay will probably want to add
yeah.
something on this.
But I'll say at least a little
Why
more.
is the number theory used as one of the foundations of mathematics?
Okay. Yeah. Well, I guess, so one question here is, not saying.
I'm being very serious.
Yeah.
Actually,
So first of all, I don't want to get trouble with you and Streetcar. And so here I was just focusing more on the connections with topology. But that's just, a scope of the talk thing. And in no way says, well, and in fact, you do get things like, let's say in Topos theory, you naturally get a natural number object, etc. So number theory is present here. In fact, one of the original reasons for doing topoi, which Shrikar could give us a whole talk on, was actually in order to do number theory topologically. So in essence, what Vade and Grothendieck did was to add a column to a table called number theory. I just haven't put it in that or Gödel in this talk for reasons of scope.
Thank you.
Yes, but absolutely there could be there is actually a column called number theory, even if we're not showing it. Right. So now, however, I'm going to add another column called geometry. So point is that, in the last thing I told you a little bit, give an intimation of how type theory is actually connected up to category theory. All right? But now category theory, historically, as I said, arose actually from doing geometry. In fact, it even arose from actually trying to do number theory geometrically. Literally, that's what happened. Actually, more accurately, it arose from geometry and topology because MacLean and Eilenberg were doing topology, and they found category theory as a way of, formalizing what they were doing. But then Grothendieck wanted to prove some interesting conjectures of Vade relating to number theory, and realized that category, and invented a notion of topos just to do that, to find a way of treating numbers as geometric spaces. And then Levere came along, as I said, he tried to say, well, how could I relate category theory to set theory and logic? So somewhere in that, there should be a relation of logic to geometry. And so now I'm going to give a little bit of a dictionary. So basically the idea is, maybe I should say how, so if we take our idea, so now the point is, I said I have functions from A to B, right? Well, one kind of function, and that was Kolmogorov's idea, that I want to have witnesses to things, and I have functions. So I said one interpretation is, well, we have functions in lambda calculus. They're given by lambda terms, and that gave us the Curry-Howard picture. Then, another thing is, well, we have a notion of morphism in category theory. That gave us what Lambek and Scott did when you apply it to logic. But there's the other place we know functions from all along, which is geometry. I could have a geometrical space, maybe a circle and a line. And I can have a map, that say projects the circle onto the line. So the question is, well, could you use those to do logic? And the answer is yes. And in fact, when you use the category formulation, you see that they look quite similar. So here's what the table would look like. So like I said, a proposition, remember we said the proposition corresponded to some kind of type of witnesses. So now let's think of that collection of witnesses as some points in the geometric space. And if your propositions are ones about geometry, that literally makes sense. If not, maybe one could, use a more generalized notion of space. All right? Then a witness would be a point in that. Then we said and, A and B, that would correspond to a product of spaces. All right? Or would correspond to a core product or disjoint union. And finally, implication. Well, implication, as I said, was, functions from one to the other. Well, in geometry, we have that. Given two space, I can make a, let's say in algebraic geometry, I can have something like the space of all mappings from one to the other. Not so much in differential geometry, but in algebraic geometry and topology, you definitely have such spaces. We have them in differential geometry, but they may be infinite dimensional. But never mind the details. Usually you can view, given two spaces, you can view the mappings in them as being some other kind of space. So the general idea goes through there. All right? So that's all I'll say for that for now, for lack of time. So I have about a half hour, and I will finish on time, because the slides are getting less dense. The sections are, especially as notions get more advanced, I get more sketchy. So then next I want to say, so most of what I was saying so far relate to propositional logic. So now I want to say a few things about what happens to predicates in this more general way of thinking. Now, as I said, originally, Kolmogorov and had a notion of the predicates all and every, but as I said, it was, even though he was thinking constructively, it's actually been improved on. Yes?
You're still limiting yourself to first order logic.
Yeah. That's right. First order logic, yes. Yeah. So, as I said, really, when you think about all and every, makes sense in classical 19th century logic because they're supposed to give you truth values back. But in the new, in the constructivist vision, you're supposed to gain witnesses instead. So obviously this may not be the best, may not quite be what you want for quantifiers. So the way you do it is, now here's the pi I showed you before, but now it actually typeset properly. So instead of for all, we're going to use this guy pi. So remember, pi it is just a product. The idea being that, p of x was type of witnesses to the proposition, p of x. Okay, type of witnesses for the proposition. Then if I took over all x's, that if I want to show something is true for all x, I should for each x produce a witness. So my question is, well, what's the type of those? So it's obviously going to be, well, I have the witness for the first x times the witness times a possible witness for the second x times the witness for the third x, etc. So that's my type. Now, actually, depending on your setting, it may be even a little more, refined than that, in the sense that suppose I was only dealing with continuous map. See, if I'm constructive, I want the way the thing depends on the witness for a proposition of x to depend in a constructible way on x. So I may only want, constructive functions in there. But if I use the notion of product, that's, right for whatever category I'm working in, of constructive things or whatever, that product will only have those in it. But even without that remark, the point is, in some sense, if you just think of the fact that I want a witness, saying for all x, a witness clearly gives me, a witness for every x, and therefore in that sense, if I take the product of witnesses for the first x times witness for second times third, intuitively I would get a witness for the whole statement, for saying that's true for all x.
And you're not assuming finite.
No. Well, that's right. Well, in the finite case, it's exactly just a finite product. In the infinite, I have to be a little more careful. Because like I said, if I want to be constructive, I don't want arbitrary things. I probably want only things that can be given by an explicit lambda term, say. Right. But the point is, if I use the categorical notion of product in the right category, that will give me only, the product will only include those constructive things. So I'm saying I can reinterpret the notion of product more generally to be only constructive things or only continuous things or whatever is relevant. Well, let's say I imagine my x's have a topology. right? That they're, let's say, of the real line. Suppose I want to prove a proposition in real analysis that says for all x in the interval 0 to 1, something happens. So then I want my witness to depend continuously on the x. Since I have the usual notion of topology or nearness in the interval.
Understanding that you bring in notions like continuity that are not defined in this context.
Right. Well, what I'm saying is this can be generalized to include them if you have them around. I'm not saying you have to have them, but I'm saying if you have them, this thing is flexible enough that I can, if I define pi properly using category 3, it will respect that notion.
Got it. Right. It sort of generalizes to whatever you put inside of it.
That's right. And speaking of continuity, for example, one of the important things Scott did was actually to show that if I want to make an interpretation of lambda calculus as functions in general, I actually need to introduce a notion of topology and continuity. That was his so-called domain theory. So, yeah.
Can I see the table right above for a second?
Yeah, sure. Yeah. Take a few minutes. Yes, and I'll email you the
slides, right?
Yeah, no, this will go online.
Okay.
Yes, this is all online. I'm gonna put the version I have now on the website, put a link when I get home, and then about a month I'll have an improved version with examples and pictures that will,
Okay, yeah. Actually, if you just put a link on our meetup page, then.
No, that's exactly what I'm going to do tonight.
Great, excellent.
Yeah, the HUD book is online.
Yeah, the book is online. It's on Planet Math, in fact.
Yeah.
And this I will put up on my server tonight, and I'll just send you a link once I put it there.
Excellent.
Maybe I'll.
If you didn't write everything down, don't worry. It's going to be there.
That's right. But have you? Yeah. Okay. So, and now similarly, if I do, instead of exists, constructively, I should give you a specific thing. So I should tell you, which x, and here's the thing that does it. So all possible witnesses or anything that, any pair where x is one of the elements of that, and w is a witness that p of x is true for that x. So here I have the type of all such pairs. All right? Right. And now, sorry?
You're only getting one element that can be any of the types.
That's right.
That are possible out of that.
That's right. That's right. Yes. So now, Levere, I mentioned, made the connections of logic to, set there. Notice there's a very interesting way of actually introducing quantifiers. So here's one which we actually haven't talked yet in our group, but it's coming up in the book. So I'll put it here first. So notice that, not surprisingly, a certain deep relation between quantifiers like exist, for all, sigma and pi, and substitution, which is a basic operation of lambda calculus. All right? So what he said is the following. Look, suppose I have a formula that depends on x and y, or a predicate. Right? Let's say x is less than y, or whatever you want to be. All right? Then he says, well, I can apply a quantifier to one of the two variables. So first of all, we assume that both x and y will range over the same domain, whatever that may be. And so I can quantify over one of them with an all and exists. And all right. And so he called that exists p of capital phi. Well, so I should say, yeah. So as a notation, first of all, I define p to be this, sorry, it's a little jumbled, but projection map saying from two copies of that domain A over which the variables go, this is the one that picks out the first one. And by capital phi, all I mean is that instead of this proposition predicate, I'm given this is the actual graph of it, the set of all x and y such that whatever that formula is holds. All right? So what he notices that now if I introduce this mapping, so this is kind of a, so now if I have this projection, I can obviously form the inverse. So given a set of elements of my domain, I could say, I could form the set of all pairs which have that as their first element. All right? And, if they have that as first element, then obviously going from that to the other is a substitution. Now, what he noticed was that then there's an interesting relation between this simple operation, this p, and the quantifiers. Now, I haven't described what an adjunction is. Those who know category theory, like Jay, will know it very well. But if for those of you who don't worry, let me just say the basic thing is that one way you can read this formula is the following. Suppose I have from one of, so it's phi and psi are graphs of two place predicates. All right, and I'm saying given any mapping from phi, big phi, to the preimage of the P1, what it turns out is I can turn that mapping uniquely into a map from the set of, there exists the X such that this to that, and vice versa. And there's a similar thing for all, except that now instead of mapping, here I went if I were mapping from the preimage thing, P inverse of phi, to phi for any such map, I can convert that map uniquely and reversibly into a map from psi into this for all. And if Jay, would you have any other way of explaining what this is?
Lost here.
Okay. Uh-oh. So then I definitely better slow down a little bit. Right. Well, I'm just trying to explain what an adjunction here is without having to make a lot of definitions.
Srikar can do it off the top of his head. Yes, he can.
Is he here?
Yeah, he's right there.
He's going to do it, but he can't.
I mean, yeah, I'm just thinking how to say this. Right. So, I mean, one way of thinking is that, injunctions, roughly speaking, if I have something, object, that if I say mappings into that object, actually it's not more than that. I have a function, one function, like in this case, this P inverse, which takes all the pairs that have the thing as their first element. And I have this other function, the exists thing. So what I'm saying is if I have a mapping from anything into the function of something else, that corresponds to a mapping from the other function into this in a unique way. Yeah.
If he doesn't do it, then it's not constructive.
Right.
No. We trust that we've got the operator in car. We trust it.
I mean, we actually need to produce.
Yeah.
Right?
Sure.
So there is some operator.
Yeah.
Called with these proof systems.
Yeah.
Where you say, I'm not going to offer you a proof that you're going to check.
Oh yeah, and Lean has a really cute. Lean has a nice snarky name for it.
Be a little bit of code, and you'll believe me. That's actually true.
Yeah, Lean has a snarky name for that thing. Lean has. I forgot what it was. Gershom remember, but anyhow, well, what it is. But what I'm saying, what this is saying is, in general, that if I take this P, which is a substitution.
Wait, that is an adjunction.
Yeah, it is.
Okay.
That's right.
I believe it.
Yeah. So it's between substitution and quantifiers.
Right.
All right. And in fact, then Wraith and Koch actually have a nice generalization where they took all the quantifiers, so both the old-fashioned exists and for all, and these new crazy sigmas and pi's, and they noticed that actually, there should be an arrow going. This should have been an arrow going down. I didn't get the LaTeX quite right, but the point is that you actually have, if you introduce the so-called slice category. So the for all I said were, with this thing I was saying from all sub things, then there's something called slice category. It's the construction where, given a category, I make a new category whose objects are some morphisms of the old category. Using a similar construct, whatever that is, using that construction, you can also get these new quantifiers, sigma and pi. The ones that give you not just values true and false, but give you all the witnesses.
There's a tiny exercise in Emily Leo's book, which is available for free on the net.
And we can bug the author in 2 weeks if we can solve it.
2 weeks. Emily Leo. She's a hotshot category theorist.
Yes.
She's going to speak as a composer.
Yeah. Right. Yeah.
So I appreciate the value of actually constructing something that exists rather than just believing that it exists.
Sure.
But there's a lot to be said about being able to prove something about something that exists without actually producing it.
Agreed.
Okay.
That's right. I would say for me, I think of constructors, by the way, not so much as a philosophy, it must be this way, as just a nice distinction to make. That when I can construct it, it's good to note that I can. But it doesn't mean I'll reject it. Just means I'll note that's constructible and maybe constructible in more than one way. Sure. Yeah, absolutely. Yeah, and that's the nice thing about saying category theory, that it lets you do both and slide between the two of them as appropriate. So, okay, so this is, so they showed that basically this is a diagram where there should be a pair of arrows and they're all adjunctions. So these are the trivial adjunction that, given a sub-object, gives you the obvious, since it's a set of arrows, I can view it as the thing, the slice category, and vice versa. These are some trivial things, but the trivial mappings. And actually, I'll put it. Okay, so now, so I'll just leave it at that without trying to get too much into it and explain what a junction is at this late hour. So in the last 15 minutes, I'm going to go back now to say something about the geometrical picture that goes with this. All right, and now maybe I'll use my little doodling thing in a moment. So, as I said, the analogous thing we have in geometry, that if you look at the category theory that goes behind this, the analogous thing would be so-called vibrations. So let me just say draw a picture of one of those. Here it is. Let's see, file, there should be a new page. There we go, let's make a new page. Good. Okay, so what often happens in geometry is a situation like this. Yeah, well, okay, that's the forgetful functor, which we don't want to use yet. So we start with a space, say a circle. Then we're going to construct a new space by saying to every kind of point on the circle, let me associate another space.
Hair.
Something like that, yeah. Circles can roll here, that's right. So a simple way.
I thought at first it was going to be a foot.
Yeah.
It's like a steaming potato.
Steaming potato, right?
Yeah.
Baked potato?
Potato has been sitting too long in the kitchen. It started growing, sprouting. So every point on the potato is sprouting a line. And this is what we call a vibration for the obvious reason.
Is this a one-dimensional, two-dimensional, three-dimensional?
Well, the circle is one-dimensional. Each fiber is one-dimensional here.
But these fibers are connected to the one-dimensional object?
Yeah, they are.
Okay.
Yeah, I mean, in this case, let's imagine, it doesn't really matter because really one should imagine them as a separate thing with a mapping to it in the spirit of what we were doing in type theory. Yeah, it could be. And it could even have cases where the dimension varies from point to point at the level of generality we're speaking. However, another thing is that this was quite simple, but one could have other examples which you've probably seen before, like the so-called Möbius strip where you have a fiber per point, and I'm not going to draw this well, but imagine as you go around the thing, they twist. So they can have those. So these are more trivial. So again, the base space is still the same circle, and the fibers are still lines, but as I go around, I don't just connect them parallel to each other like I did here. I now allow them to twist around. So they might twist once or more and then reconnect. So this is a general notion of what we call vibration. Yeah.
Moving towards the notion of cap.
That's coming.
Okay.
That's going to be the very last thing. Yes. Yes, that's coming. Yeah. Sorry.
Do these fibers connect up to other circles, and thus you're projecting from here to there? Or
well, you might. Yeah. Well, here I'm.
Just exist as is. The fibers just go.
Right. Well, I guess the way we imagine is, I have one space which is made out of fibers, and then that projects down to the circle by giving each fiber the point associated to each fiber, whole fiber a point, single point on the circle.
The fibers form a sheet.
Well, okay. There is a yes. They're very closely connected to sheaves. I didn't want to go down that way because it could take a while. But actually, sheaves would be more what happens if I took a part of the circle. Let's say I only took this little, well, no, I don't want to erase it again. Let's say I took just this portion here, right? Between here and between these 2 points. So I take that portion, or let me draw it here. Let's say I take the portion that lies between this point and that point. Then I could have, take that sub subset of the circle and the fibers that go to that. And I could repeat that for other subsets. So that would be, the sheaf would actually be the structure you would get where if you took all the different open subsets and the fibrations over those.
All of them are all possible ones?
Yeah, you would take all possible open sets, and for each open set I have the restriction of the fibration to that open set.
It's like a power set.
Yeah, well it might be, but it may not be all the power set, because I may only want open sets.
Oh.
So for example, I don't want a closed subset of the circle, only the open ones, yeah.
You get a local product.
Well, I mean, in this case I don't, okay, oh, you're saying, yeah. Well, that's right. The usually nicely behaved, you're right, the nicely behaved bundles here say that, yes, given a point, I can find an open set over which it looks like a product.
Are we necessarily using continuous one-dimensional circles?
I mean, this example I am, but in general one doesn't, it's much more general than that. Yeah, they could be discrete. Okay. I mean, the most general form would be I just have an arbitrary set B, an arbitrary set B, and fibers are just sets. But if I have more structure, I may want it to preserve that. Like if I have topology where it's continuity, then I want my fibers to actually preserve that structure.
So to every point of the circle that corresponds to one of these fibers?
Yes, that's right.
Yeah. And it may be that the fiber may process it from the other side?
Yeah, sure. Well, so the way we imagine this is actually kind of our type theory where we imagine the fibers as, strictly speaking, being a different space than the circle. So I can just imagine, I have explicit projection map. I mean, I could have a concrete one where I say, yes, they actually cross the circle at a point, but in the spirit of what we're doing in category theory, we want to keep it a little more abstract and not actually, assume they're in the same, they're actually the same elements, the same thing, but give us expression projection mapping P.
And you're saying
projecting from the fibers?
Well, from the totality of all the fibers. So a space would be something like either a cylinder or a Möbius strip. Then I could let me imagine my circle is a separate thing. So I'm going to project each point on the fiber down to a point on the circle.
Is it like a vector space?
Well, it's more general, see, because if I have a product, projection onto a factor would be an example of this. But the whole point of the Möbius strip was that's an example where it's not just a factor, because I had the twist in it. So in the factor space, I had two projections, let's say in this, where I could project to a circle, I could project to a line. But if I have a twist, that projection to a line is no longer there. I only have the projection to the circle left.
You still have the local.
Well, if I have a local structure. Here I don't even need that. When I have that, which I may not. I may or may not have it locally. Here I don't require a factor structure even locally. I mean, I could have one, classical geometry you would. But at the level generally we're talking, that's no longer assumed. All I assume is that I basically, some projection from E to B where, like I said, E to B could be cylinders and circles, but they could be just two arbitrary sets, and P could be an arbitrary mapping. All right? So in terms of this, with our sigma pi, I'll just state it that sigma of this thing P would be then correspond to the total space, that is the space that all the fibers live in, or comprise of all fibers, and then P is a section. So what's a section? Well, let me explain that. Let's show the picture here. Where was it? Okay, so suppose I pick a choice of point for each fiber, right? Let's say this point here, that point there. So that'll give me another circle. That's called a section.
Oh.
And I could make a different choice, and that'll give me another section, etc. So as I said, if I literally imagine the fibers correspond, that would mean I had a preferred section, but which I may or may not have. Yes?
Can you draw from any point on any fiber to any other point, any other fiber, or is it sort of parameterized where you would always want it at the same point on the other fiber?
Well, see here, there's not necessarily, in general, there's not a notion of same point. No, in general, unless you have something extra structure like a connection in geometry, there's no way of really comparing one fiber with the other. And the way we're thinking in type theory, we're saying the different fibers, when we think of these dependent types, may even be of different types. And hence there would be, it may even be impossible to really say they correspond because they're totally different types. I mean, classical geometry, sure, they're all, of the same type, and you can introduce structures that would allow you to do that.
Let me just say,
Yeah.
there's a whole bunch of concepts here.
Yeah.
And they're formally quite different. Under various hypotheses,
Yeah.
you can sometimes pass from one to the other. So you'll have one structure here, and then you'll suddenly say, for example, for a sheaf. Under some circumstances, you can realize it as the sheaf of local sections, say, of some bundle. Other times you can't. They're all closely related, though.
Yeah.
And the pictures, without further words,
Right.
don't single out,
Right.
which concept you're talking about.
Right. That's right. Yeah, and usually pictures are drawn from, ordinate geometry because that's what we know how to visualize. And that's where these notions came from, but then what you do is you write what is it, you write what are the algebraic properties of it in category theory, and you get something that's much more widely applicable to situations which you may not even know how to draw.
So it's more important that they connect. There's no distance measure.
No, there need not be. There need not be, and if we're doing logic, there probably wouldn't be. It's not immediately obvious if I'm doing propositions why I should have a distance measure there. So, all right, so I mentioned that. Okay, so now, so that's, okay, I'll leave it at that for now, especially since I only have only a few more minutes. So I'm going to do what Pierre was asking now, get to the role of paths. Because we know if we're doing spaces, the obvious thing is, what about paths in those spaces? And so I'll go about it, again, by starting from the point of view of logic and then building up to geometry. So in logic, we also have a notion of equality. And the basic property or equivalence, whichever you want to call it. So basic property of equality equivalence are three of them. Reflects that anything should be equal to itself. Symmetry, it doesn't matter whether I say x equals y or y equals x. And it's transitive, that if things are equal, I can combine them, substitute them. So I guess transitive, I should have said also as a generalization that in fact, if I take any proposition of something and I substitute equals, I'm still going to get back equal propositions. All right? So those are basic property. So now let's think in the land of type theory how one would implement this. So now we want to have witnesses. So what we say is that if I have a type and I have an x and a y that belong to, obviously I should only be able to talk about equality if things are the same type. Because as we said, the whole principle of type theory is that things that are different types are just totally disjoint worlds. They aren't reigning, so we couldn't possibly, what would it mean for them to be equal? It's probably not even a well-posed question. Yeah. So we pick an x and a y that have the same type. Then I say, okay, well, let me make a new type which is witnesses to their being equal. And this is non-trivial because imagine I was doing some algebra. X and y might be algebraic terms, statements. Well, proving they're equal might involve, a lot of work, right? I have to factor the thing and move terms around, factor it, expanded a lot to prove that yes, these two terms are actually the same thing. They don't look all the same. It's non-trivial to show. Yeah. After all, math journals are filled with long papers where people take 100 pages to prove two things are equal. So it only makes sense that I should take that fact into account. You wrote me x equals y. That was a 100-page paper to show me. Yeah. So the type. So that's what I mean by this type of equality is the inhabitants are these 100-page papers that show me they're equal. Yeah, okay. So now we want to say what are the, how do we, so we say, okay, there should be this type for equality. So what are the basic assumptions we need to make in type theory? There's basically two of them. One is that, as I said, we want anything to equal itself. and it should have a trivial proof that n equals itself. If I write x down, x equals x is there. I don't need 100 pages to tell me that. Right. Unless I'm some smart Bourbaki guy trying to weed out the newcomers, but that's another story. So, all right, we have this what we call REFL, which is simply a witness to the fact that x equals x. Then I also have an induction principle, and stating it generally it's kind of complicated. That's what they do in chapter 2 of the hot book. But in a simple case, it says if I have some proposition C of x, x holds, which of course means I can find a witness to it, then then I should be the case that Cxy will hold whenever x is equal to y, which constructively means that if I give you a witness that x equals y, and I knew that, and a witness that C of x is x, I should find a witness for this. All right. And then, however, now we get into something is all familiar from Lisp, right? Once you make, the nice thing about making everything, first order, like functions or whatever, you can then use them further. So here, with types, we kind of did that. We made equality explicit in the sense that we said there's a type of witnesses to equality. Well, that's a type. So let me repeat the process. Suppose I have two witnesses to equality. I can ask the same question, are they equal? And I can make an equality type for that. Non-trivial because, like I said, suppose in my math journal I had 100-page proof that these are equal. Then I have another proof that maybe uses totally different techniques. I might say, well, those are two totally different proofs, like what we said. And yes, so therefore I should have a case of non-equivalent witnesses to equality. They both show that the original things are equal, but they do it in totally different ways. And there are geometric, all right. So we have that. And now comes the paths. We can interpret, if we think geometrically, the way to think of a equality will be as a path. Because metaphorically you would also imagine, I start with A, I want to show it's equivalent to B. I might, because of transitive, I can do it step by step. I show it's equivalent to something nearby, that's equivalent to this, that's equivalent to this other thing, and eventually I got from X to Y.
So you're drawing field lines of equal potential.
Well, sure. Yeah, for example. Yeah, that's right. That's right, because first equality is defined locally. For nearby points, I can see this is the same potential. And yeah, you follow it out, you get something like an equal potential line. That's exactly the image we have here, which we're going to use more exactly. That's right. And then, okay, so like I said, and again, we can also think of them, and this goes back to your equipotential thing as a space, right? Because let's say I had my three-dimensional thing. Each path, equipotential path would be one equality thing. Well, they might span out a sphere, of all the different ones. So all the equalities actually then form a new type, or as a new space. All right. So which is a path space, which is something that topologists know very well. It's a standard construction. Give them a space, I construct the space of paths of that space. All right. Then now, okay, yeah, here. Sorry. Yeah. So the next thing I was saying is that let's say I take a function of a path. Then if I think what this means, it means that the function lifts the path in the base space to a path on the bundle of it. Which is again a very well-known operation for basically a classical thing everybody does in differential geometry. And finally, what I was saying higher paths is, what I meant by higher path was, logically it was this idea of, well, given two proofs of equivalence, how do I go from one to the other, show that they're equal? Because they might be quite different, or they might not be. Well, geometrically that would correspond to, if I have a path between A and B and another one, a path joining them would, let me go back to my doodler here, right? If I have a path here, another path here.
There's the two endpoints.
Right, this is P and Q. Some kind of P and some kind of, up to topology that's a P and that's a Q. All right? So then a path between paths means, well, means a one-parameter family of paths, right? That start on the first path and end with the second one.
Form the one path into the other.
Yeah. And what does that do? That traces out a surface.
Yes. Got it. Wow.
And then if I were to have an equality between two of these things, that would trace a three-dimensional volume, etc. Now, the point is that this operation is, again, also very well known from topology. That's, in fact, what most of homotopy theory deals with, is exactly this thing. If I have some object, I make a, as I said, make a one-dimensional deformation of it, which could be a path. So, for example, this way you would start with a point. I take a path of points, I get a line segment. Take a path of those, I get a square. Path of those, I get a cube, etc. That is a classical way of building topology. And so what was interesting about the HOT project was, when a topologist came along and seeing this, was able to take all kinds of constructions from topology, like Postnikov towers and whatnot, and show that, yes, those could also, be backported into logic and category theory. So I'll end with that, so at least it gives a flavor of what the heck homotopy type theory means. Is just this, that in homotopy theory you're studying paths and paths of paths, building up your spaces, and now the interesting thing is that this can be related to type theory and category theory and all these other subjects, as I said. So with that, with that comment, I'll end the talk. And
thank you.
I'll invite everyone. So I make a preliminary announcement.
What? Go ahead.
A quick preliminary announcement is that tomorrow night at City University, for people who want category theory, Noson Yanofsky will be lecturing about his applications of category theory to computer science. And next week at the same place, Emily Rio will be coming, and actually, who is one of the members of the HOT book, among other things, and is talking about higher dimensional category theory, which is basically how you build this notion of paths between paths, equivalences into category theory. See, there's a way of doing it, which is usually done, which is through constructions of so-called, of category of simplices and that from topology, but she wants to do it in a way which is more intrinsic. Say, if you took the point of view of this, how could you reformulate it? It would be the same thing, but formulated and motivated in a way, that goes with this way of thinking, that equivalent, that the notion is I have equivalences between equivalences, etc., not do some geometry first and say that is the thing, but rather build it up from that notion and axiomatize it suitably.
And if you can't wait, and you're just saying and having a hot conversation over a cold beer, or maybe a hot conversation over a warm meal, right? You can meet us at Flight 151, and I think we're going to prove that there's a category of List NYC attendees to Flight 151, where we're all talking about hot, or whatever we want to talk about. So, and my other announcement too is let's be as good guests as our host has been a good host, and make sure that we clean up after ourselves. And with that, we adjourn the first part of our meeting.
Yes, and as I said, I will post the notes online.
And you'll post those.
So yeah.
It was too much. That was great.
Nailed it, dude.
Last part was too short.
Well, I don't know. I don't have.
Yes, but you're going to join us, right?
That's right.
Yeah. Okay.
Well,
your drinks are on.
Yeah, okay. Thank you.
Topos theory was used.
Well, the point is, it was sitting in the background of the book and never really got mentioned.
Okay.